large group of visitors from West Windsor, Plainsboro. I don't know if they came into any of your classes, but Mr. Tizzle is friends with one of them, and they recommended that he come here. So good job in giving such a great impression to other visitors that nets us more visitors. All right, so I'm happy to go over the homework. We are due for a quiz. Yeah, I don't think I made one though, so. We want to finish up with the first law of thermodynamics and our changes of state. I think we only did isobaric expansion last class, right? So we have to do the other 3 changes of state as well. And then we also want to kind of finish up that piece of the topic by looking at cycles, so combinations of those different changes of state. I want you to read the remaining 4 sections of the topic, right? So that's it. We're done with the topic next class. You have pieces of, I think 2 full paper 2 questions, and then a few paper 1 questions to do for homework. The labs that we collected data for last time, remember, due June 3rd, but if you give it to me by May 28th, some extra credit. And then our topic 10 test will be May 30th, and that will be like not 100 points like our topic 8 test was, but maybe like 60, 70 points, something like that. Bless you. Other questions from anybody before we address homework? Great. So I'm happy to project my book, but if you'd rather have a hard copy, feel free to grab one. Bless you. Alright, so I think number 1 was the first one. I ended up having B, that the change in internal energy was 0 joules. Anybody want to talk about that one? No? Yeah? Alright. So this one, we were given way more information than we needed. The only thing we really needed to care about was that this gas was held at a constant temperature. Right? Constant temperature means that the average kinetic energy doesn't change, and an ideal gas only has kinetic energy. So because the temperature is held constant, the internal energy stays exactly the same. Follow-up issues on number 1. Okay, number 2, I also had B. Does anybody want to talk about number 2? Yes, all right. So for number 2, we again have an ideal gas, and we compress it at constant temperature. The pressure goes up, which is the best explanation for the reason that the pressure increases. So we have number 1, the mean speed of the molecules increases. That's false. Right? The temperature stays the same, so the average kinetic energy of the molecules has to stay the same. So that is just wrong. Number 2, the molecules collide with each other more frequently. That's a true statement. Okay? We're putting the molecules in a more confined space, but the pressure has nothing to do with the collisions between molecules. It has nothing to do with the force that the molecules exert on each other when they collide. So even though that's a true statement, it doesn't help us explain the pressure increase. Pressure is the force the molecules are exerting on the container, well, per unit area, when they're colliding. So 3 is the only answer that is true and helps us establish that the pressure should go up. Other follow-up issues with number 2. Number 6 was the next one. I think I got A for that one. Did anybody want to talk more about number 6? Okay. Number 8, now I have a question mark because I didn't get the same answer as the CD file. For number 8, I got 1.5 million joules. First of all, did anybody else get that? Okay, did anybody get the answer that the CD file had, which was 1.29 times 10 to the 6 joules? Yeah, so I think you did?
Yeah, cool.
Alright, so let's look at how we get this, and then maybe Justin
Please
can
excuse the interruption. You will see a fire truck pulling up. A malfunction in the monitoring system caused an alert to go out as though we were actually pulling the fire alarm for a live problem. So there's no problem. The fire truck will pull up. You do not need to evacuate the building, but I just wanted you to know. What's happening? Thank you.
Alright, so yeah, let's look at how we do number 8, and then maybe Justin will be able to tell us what the authors of the book did. So we wanted to find how much energy has to be added to some ice at 0 degrees Celsius to convert it to steam at 100 degrees Celsius. So I thought we actually had to do 3 different things to these ice molecules. I thought we had to change them to liquid molecules. Right? We had to change the phase. And this is topic 3 stuff, right? Nick asked about topic 3. Yes, in topic 10 there was a question that was 100% topic 3. Then we have to change the temperature of the liquid water molecules to get them up to their boiling temperature. And then we have to take those 100 degrees Celsius water molecules and turn them into gas molecules. So I did 3 separate calculations. The mass was the same in each one of these, half of a kilogram, like even once we changed the phase. And then I had to look in topic 3 to find the latent heats and the latent heat capacity and the specific heat capacity. For the latent heat of fusion, I used 3.34 times 10 to the 5th. For this one, again, it was 0.50. The specific heat capacity of the liquid water is 4180 joules per kilogram per Kelvin. And then we have 100 degrees worth of temperature change. And then for this one, we still have a half a kilogram of water. And then the latent heat of vaporization was 22.5 times 10 to the 5th. All right, so for this one, I ended up getting 167,000 joules. It's kind of a lot, and I gave that 2 significant digits. This one, 209,000 joules, also 2 significant digits. And this one, 1,125,000 joules, also 2 significant digits. So when I added them up, I did get 1.5 million. So Justin, what did you do to get the answer that there? What didn't you do?
Well, I did a dumb mistake, and instead of 209,000, I got 20,000 instead. So when I added them together, they got around 1.3. So that's how I got it. But it was just a dumb mistake.
So that to me implies that they did. Did you get 1.29 or just
it was
something?
It was like 1.3. So
all right. So I don't know if that's what the authors did or not. Any other issues with number 8? All right, and then finally number 9, I got negative 6.4 times 10 to the 5th joules. Negative 6.4 times 10 to the 5th joules. Did anybody want to see number 9? Okay. So for number 9, we have a gas, presumably an ideal gas, that is heated. So we're delivering thermal energy to it. It expands and it does work to the surroundings, and we want to find the change in internal energy of the gas. So we're definitely using our first law of thermodynamics. We do add heat to the gas, so positive 1.68 times 10 to the 5th joules is the Q. The change in internal energy is what we want to find. And then we are told that the gas does 8.1 times 10 to the 5th joules of work on the surroundings. That means that the work is a positive quantity. It's 8.1, right? Okay, so all I had to do next to solve for the change in internal energy was subtract the 8.1 times 10 to the 5th from both sides. So I got negative 6.4 times 10 to the 5th joules. That means we removed energy from the molecules of the gas, which maybe is a little bit weird. Maybe that's weird if we're removing energy, yet the gas is still expanding, but nonetheless, that's what we get from this scenario. So we add heat to the gas. Some of that heat, actually, probably all of that heat goes to do work, but then we're also extracting energy from the molecules to do even more work. Other issues with number 9? Okay, great. Do I have anything? I do have quizzes from last time to get back to you, and then let's just take a look at our remaining objectives while I'm handing those back. So again, we want to continue to describe our changes of state of an ideal gas. We want to continue to draw and annotate those processes on pressure versus volume diagrams. We want to continue to calculate work done from those pressure volume diagrams. And then we want to, and from cycles as well. And then just generically continue to solve problems. All right, so I'm going to give these back, and then we'll get into that. What time are you next to go?
It says 12:10.
Okay, great. That is not you. I take it back. Nick, can you turn all the lights on for me? All right, so we did well on the quiz. I think everybody was able to identify each of the symbols in the equation of state of an ideal gas. Some of you neglected, a few of you had neglected to identify the gas constant. Units were fine as well. And then on your version, number 2 was an ideal gas should be at low temperature, and that's false. If the ideal gas is at a low temperature, it might be close to its boiling point. It might be close to becoming a liquid. So that's incorrect. An ideal gas should be at an elevated temperature. All right, any other questions with the quiz or the homework or anything else before we continue with our state changes? All right. So we already went through this isobaric expansion, as I recall. And remember, we have 3 equations now that are helping us either describe the state of a gas or determine information about work or internal energy changes about the ideal gas. So we had our equation of state. We have our work is pressure times change in volume. And then we have our first law of thermodynamics. And the main thing that I want to continue to do today is to make sure that for each of these processes, we can determine in our first law of thermodynamics whether each of those terms is 0, positive, or negative. All right, so we've already done that with the isobaric expansion. I am recording today, not so much for Robbie, but for the class tomorrow, because I'm not going to be with them. So you guys, this was posted already, so you might need to go back and look at that video that was posted. So we'll go ahead and do the isobaric contraction pretty quickly, since we've already done our isobaric expansion. So isobaric meant same what? Pressure. Same pressure, right? So anytime we have an isobaric change of state, that has to mean that the pressure stays constant. And all that contraction means is that the volume decreases. So on our pressure versus volume diagram, that's just going to be a horizontal line, just like it was last week. But this time we'd be going from higher volumes to lower volumes. All right, so let's go ahead and attempt to tackle each of the terms in our first law of thermodynamics. Is any work done?
Yeah.
We have a non-zero pressure. We do have a change in volume. So yes, somebody is doing work to somebody else. And the surroundings are doing work to our system in this case, right? Because the surroundings are pushing in and making our system smaller. So we call that a negative amount of work, right? If the volume change is negative, the work has to be negative. So our work done is negative. What should we do next? Let's do the change in internal energy next. What other quantity did we need to look at to determine that? What did we do last week? Yeah, temperature, right? So if we look at our equation of state of an ideal gas, we know that our pressure changes, well, pressure is not changing, right? That doesn't change at all. The volume is going down. We don't ever lose or gain gas, right? We're not letting gas leave our system. So the number of moles stays the same, our constant obviously stays the same. So if the volume decreases at constant pressure, the temperature has to decrease. And that has to mean that we're extracting energy from our gas. Right? The molecules have to be losing energy to the surroundings, so our change in internal energy is negative. Let me do a pause for a minute and ask if anybody has follow-up questions about work being negative because the volume was decreasing, or the change in internal energy being negative because the temperature has to decrease if we're decreasing the volume at a constant pressure. Great, so is the Q positive or negative? Negative. It's negative, and in your groups real quick, can you just make sure that you remember what a negative Q means, right? So in your groups, at least, hopefully somebody remembers what a negative Q like means. Yes. I gave you extra? Well, I'm not gonna take them away, but oh, Paul brings up a good point about your quiz. I actually didn't even look at the units you guys put on for the ideal gas constant. So, like, you may have put it wrong, and I just didn't even look at it. Like, I didn't count that as part of the quiz. So yeah, thank you for reminding me of that. All right, so negative Q means that heat goes from who to who? From the surroundings, wait, what was this? From the system to the surroundings, right? It's positive Q if we're delivering heat to our system, so it's negative Q if we're taking heat out of our system and putting it into our surroundings, right? Which, and yeah, so whatever. So in an isobaric contraction, negative work, so the surroundings do work to the gas, negative change in internal energy, so the gas molecules lose energy, and then negative Q, so we're removing energy from the gas. Follow-up questions right now about isobaric before we move on to our next one. All right. So our next one is isochoric. Now, so iso obviously still means same. We don't actually need to know what choric means because on every question I've ever seen, they put isovolumetric in parentheses. So in an isochoric change of state, the volume is staying constant. So the first one we're going to do is an isochoric increase in temperature. And we need to depict that on our pressure volume graph. So can you, again, consult your neighbors in your foursome and see what you can come up with for what an isochoric increase in temperature is going to look like on here.
Volume is essentially just like the volume
Don't exclude Shankar, please. Shankar.
increase.
If we change the temperature, does the pressure change or not necessarily? I think it has to. So the volume does not change, the pressure does, so we definitely have a vertical line. And if we have an increase in temperature, would the vertical line be trending up or trending down? You sure? So we're going to have to consult our equation of state of an ideal gas. All right? The volume is increasing. Oh, wait, no, I'm sorry. The volume is not changing. The number of moles aren't changing, the constant's not changing, the temperature's going up, so yes, absolutely, the pressure has to be increasing. So yep, it's going to be a vertical line that points up. I think that's what all of you, or at least most of you, came up with. And so we've got the sketch. Now we want to go ahead and address each of the terms in our first law of thermodynamics. So let's do work first. All right? Choices are 0, negative, or positive. So raise your hand if you think work is 0. Got like 4 hands. Work is negative. No hands. So positive? A lot of you think positive. So work is pressure times change in volume. We do have a non-zero pressure, but the volume is not changing. The change in volume is 0. So there's nobody's doing work to anybody. We're only doing work if we have a change in volume. So no work at all. Okay, no work at all. Follow-up questions about that. That was not obvious to all of you. Elizabeth, you're giving me 30 looks, but you voted for 0. You're okay, fine, all right. All right, so work is 0. Change in internal energy, right? 0, negative, positive. Take 10 seconds to decide. If you can't, I'll give you your 10 seconds first. If you can't decide that, then you really do need to go back and look at some of the earlier objectives, like in 10.1, because this should be pretty straightforward. The temperature is going up for an ideal gas, temperature and change in internal energy have to do the exact same thing. So we have to have a positive change in internal energy. The temperature, right, increase in temperature, delivering energy to the molecules, they have more kinetic energy, right, internal energy is going up. All right, and then the last thing we need to assess for the first law of thermodynamics is our Q. So raise your hand if you think, nah, go ahead. So I'll feel bad. It's got to be positive, right? We're taking a positive quantity, we're adding it to 0, so it's got to be positive. So we are delivering thermal energy to our gas, we're delivering heat to our gas, but all of that heat is going to increase the temperature, none of that heat is going to expand the gas. All right? So that's an isochoric increase in temperature. Follow-up questions with that? I'm going to go lightning fast through the isochoric decrease in temperature because, well, everything's just the opposite. I'm mildly worried about the camera filling up. Alright, so this is just what we already did, right? We said isochoric is constant volume. We did sketch on the PV diagram. Normally, because of the ideal gas law, if we increase temperature, the volume increase temperature, at least some combination of these has to increase. We're holding the volume constant, so the pressure had to go up. We said the work is 0 because the volume of the gas is not changing, and we said the delta U, the change in internal energy, is positive because the temperature is going. Okay, for the isochoric decrease in temperature, the only difference on our diagram is that we point down. That should be straight down, it's a little sloppy. If the volume is staying the same, the work is still 0. If the temperature goes down, the change in internal energy is negative. We have to be removing energy from those molecules, and then we have to be taking heat away from our gas. All right, so let's go to the next new one, which is an isothermal process. So same what? What's the only thing left to keep the same? Temperature. Right, temperature. Temperature staying the same. And we're going to do an expansion, so same temperature. And we're going to do an expansion, so the volume is going to have to increase. All right, foursomes. Sketch it on the PV diagram. Sketch on the PV diagram. Oh, sure.
Oh, wait. Volume's all really awesome. Oh, wait. What's the increase? What's the increase in your What's the increase in your Oh, no. Temperature. Okay, yeah, that's volume. Volume? Yeah,
All right, I want you to actually use your graphing calculators. If you don't have one, if you have one in the back, get it. If you don't have one, hopefully somebody close by does. Alright, so for an isothermal process, the temperature has to stay the same. So using our equation of state of an ideal gas, everything on the right-hand side is staying the same, right? Even though we're changing the properties of the gas, everything over here is constant. So what we're left with is that pressure equals some constant divided by volume. So what I'd like each of you to do, if you have a graphing calculator, is pick something for your constant. Pick something positive, negative. Well, it can't be negative. Pick some positive value, small, big, whatever, and graph y equals that constant over x. And whatever the heck that looks like is what our pressure volume graph should look like. Right, so whatever you pick, you see what that looks like, but then look at what other people's looks like also. They should all look pretty much the same. God. All right, if you have not got yours yet, so lots of you do, if somebody's done it. Cassie, you used a large constant or a small constant? So, I mean, well, on your calculators, we're seeing that, but we're not going to have negative volumes, right? Or negative pressures for that matter. So we get, what do we call that? I don't even know. That doesn't have a name? An asymptotic curve. I feel like we could have other asymptotic, whatever. Well, in this context, we actually call that shape an isotherm. But that's absolutely what we'll see in terms of pressure and volume. Now, if it's an expansion, we would be going from smaller volumes to larger volumes. So maybe put our arrow over here. So that's what our pressure volume graph would look like. This would be at one temperature. Right? Now, you guys did all kinds of different constants, but you still had the same type of curve. So we would just have these nested curves for other values of temperature. So these would just all be isotherms. These would just be isotherms for different temperatures, right? Isotherm A, isotherm B. Each of those isotherms would correspond to a different temperature of our gas. I'm going to erase that for now. Questions from anybody on the variation looking like this? Alright, if you ever forget what it looks like, just use your calculator. So let's go ahead and go through our first law of thermodynamics. Is any work done? I'm hoping that these questions are getting easier and easier. The question you have to ask yourself to answer that is there a volume change? And there absolutely is. And for the isothermal expansion, it's a positive volume change, going from low volume to higher volume. So we definitely have positive work. Right, our system is doing work to the surroundings to increase its size. For the change in internal energy, well, what is it? I heard about 3 people say 0, and that's absolutely correct because the temperature is constant. And in fact, I guess it says it right here. I shouldn't have exposed that. If the temperature doesn't change, then we're not changing the kinetic energy of the molecules, and the molecules have no potential energy. So if we're adding 0 to something that's positive, that means we have to be delivering thermal energy to our system. All right? So we're giving our system energy, and all of that energy is going into work. The exact opposite of what? The exact opposite of our isochoric process. Questions on work being positive because of the volume increase, internal energy being 0 because of the constant temperature, or Q being positive because of the work? Now,
When could you add heat to a system?
without a temperature change?
Yeah.
I suppose you'd probably need, you would need a container that really didn't take any effort to make it get bigger. Do I like that answer? I don't think about that. When can you do this? I'm sure it could be done, but all 3 of the things that we saw so far are kind of difficult to do. They're extremes, right? More typically, we would have combinations where we're not necessarily holding anything constant. Maybe the isochoric would be sort of easy to do if we had a really heavy steel container and we were increasing the pressure. But yeah, I think the better question is, these are just extremes. I don't have a better answer for you. Other issues with the isothermal expansion. Now we do have one other type of state change. Obviously we have our isothermal contraction, which is just going to be the exact opposite of our expansion. The volume is going to decrease. The work done is negative since